You need to open. It's on, sir.
It's on?
Yes.
A
little bit down.
Will it come?
Yeah, down.
Ah. Good afternoon and welcome to the special asset colloquium. This is special because it is being organized on a non-Friday, and also it is special because this is a joint colloquium by DAS seminar, Department of Astronomy and Astrophysics seminar, and asset colloquium. It's indeed great pleasure to today welcome Professor Hidehiro Kaneda from Nagoya University, Japan, who is visiting our DAA department and also to deliver this today's colloquium here. On a personal note, it is great pleasure and opportunity for me on the last day of my career at TIFR to listen to a real expert on the cryogenic space telescopes. And I'm sure this must be a technology that is something going to kind of excite many of you for finer measurements. Obviously, the cryogenics is even in many other fields like nuclear and high energy has been doing exceedingly well these days, because it's very important to keep the resolutions very high. Keeping the thermal conditions under control will also help detector performance. And I'm looking forward to this exciting colloquium. Without taking more of your time, I request Professor Devendra Ojha to formally introduce today's speaker. Thank you.
Thanks, Satya. Good evening. So before I introduce today's speaker, I would like to thank Satya. Actually, it's remarkable that it's the last working official day TIFR. He is still, conducting this asset thing. Actually, that is his baby, actually, asset. And thank you for your continuous effort and dedication for making this asset colloquium such a remarkable, wonderful series. And thanks to giving opportunities to our engineers from DA and Vellum facilities who actually got these opportunities and they grow in that. Thank you very much. Let me introduce today's speaker, Professor Hidehiro Kaneda from Nagoya University. And Professor Kaneda-san actually did his PhD in 1997 from Nagoya University, actually in the X-ray astronomy. So he is actually X-ray astronomer, but then he switched over to infrared, and actually he's doing both astronomy, X-ray and infrared. So after his PhD, he joined ISAS JAXA in 1998, I think. And then he moved to Nagoya in 2008. And right now, he is the PI of Astrophysics Lab in Nagoya University. And he has almost 30 years of experience on working on various instrumentation aspect, either X-ray or infrared thing. Actually, he was the PI of mid-infrared instrument on Spica. And before that, he worked on ASCA and Sujaku on X-ray experiments. And then later on Akari, which was infrared mission of Japan. And Spica, unfortunately, could not be flown, but he was actually PI of MIR instrument as well as co-PI for other instrument. And last few years, he has been now involved in many other space missions, I think in joint collaboration with US and other countries. And he will talk about this. And he has a long association with us, almost like more than 2.5 decades, I think like 26 years. We are collaborating on our balloon-borne experiment, and he's leading this experiment from Japanese side. So I invite Kaneda-san.
Thank you very much for your introduction. And first of all, I'd like to thank organizers for giving me this opportunity. And also, it's my great pleasure to giving this topic, so the infrared spectroscopy with space cryogenic telescopes. And we have been collaborating with Professor Ojha and Professor Ghosh for a long time, more than 20 years. So mostly based on the balloon observations. So the balloon observations, and using not only balloons but also the actually, I get I do not use the ready?
Yes. Yeah.
It's a bit slow.
Yeah, it is a bit slow.
It's a bit slow. Okay. So anyway, so not only balloons but also the satellites and then the ground-based telescopes. So we are doing infrared astronomy. And today, so I'd like to okay. So today I'd like to concentrate on the space infrared spectroscopy. And here is the outline of my talk. So first, I'd like to explain what we can do with space infrared spectroscopy briefly. Then technology needed for space cryogenic telescopes, and several topics. So I'd like to select this study, so mineralogical study of interstellar dust, and finally, the future prospects. So first, I'd like to explain my research background very briefly. So actually, I started my research with solar physics using a satellite Yoko, and then I was involved in the satellite project Asuka and Suzaku, and I wrote my PhD thesis on this topic, X-ray astronomy topic, and then I joined the infrared astronomy group at JAXA, and I was heavily involved in the satellite project Akari, and the next satellite project, Spica. And actually, during this term, so I was a project deputy PI. And at the same time, Japanese instrument PI. So during this time, I was very, very busy. But unfortunately, so about 3 years ago, so the Spica was canceled due to the cost overrun problem, mostly on the European side. So that happened during the coronavirus pandemic. So it was quite unfortunate. But now, so we are promoting the mid-infrared mission called Julius Plus and the far-infrared mission, far-infrared probe, so the Japan-led and the NASA-led missions. And more importantly, so we have an Indo-Japanese balloon T100 FPS project, and I'm managing the ground-based telescope in South Africa. So first, space infrared spectroscopy. So there are lots of astronomical targets for space infrared spectroscopy, but what are the best fit, best matched targets? So I think we have two important factors. So one is the temperature, and the infrared temperature corresponds to 20 to 1000 K, so significantly lower than the sun temperature. So the radiation from the sun peaks at 6000 K, and then the targets best fit for the infrared astronomy is has a lower temperature than the sun temperature. So considering this temperature range, cool stars like young stars, protostars, and the planets, exoplanets, and the ISM, so interstellar medium heated by stars and black holes. So these are best matched targets for space infrared spectroscopy. And I think we have the other important factor, so the infrared spectral bands due to solid state particles. So physically, there is a frequency of vibrational modes included in the infrared wavelength range. So the solid particles like minerals, organic matters, and ices. So they are fundamental materials, but we can study these fundamental materials spectroscopically. So our aim is to unravel the whole story of the evolution of solid matter in space through galaxy evolution from the early universe to planetary system formation in the current universe. And this is a typical infrared spectrum of a galaxy, the typical spectrum of a galaxy from radio, infrared, and visible, and UV. So there are two main components, and this one is the starlight in the visible and the UV, and these stellar photons are absorbed by solid particles in a galaxy, and here I call this simply dust. So dust absorbs the starlight in the UV and visible, and then we emit in the infrared, mostly in the infrared and also radio. So actually, so this wavelength range is the target wavelength range. So in my talk, so mid and far infrared, or mid and far infrared cannot be observed from ground. So we call this wavelength range space infrared wavelength. Then you can see there are many spectral lines, narrow lines, and these narrow lines are due to gas in a galaxy. But not only these narrow lines, but also we can see broad spectral features. And these broad spectral features are due to solid matter. And these spectral features are mostly located in this wavelength range. So as you can see, the infrared spectroscopy, especially space infrared spectroscopy, is very important to study the solid matter in space. And this is an infrared spectrum of a galaxy. And focusing on this part, So as you can see, there is a wide variety of the spectral shape. So the rest, actually, this one. So blue spectrum is taken from the star formation activity dominated galaxy. And this red spectrum is taken from the black hole activity dominated galaxy. So depending on the nature of the activity in a galaxy, the spectral shape can vary significantly. And so there are many spectral features, so the broad features are there. For example, these features are due to polycyclic aromatic hydrocarbons, so the organic matters, so which contain many benzene rings. So the organic matters are there, and these broad absorption features, so these are due to silicate minerals. And later in my talk, I use these spectral features for scientific research. And in addition, so we see water ice, several water ice features, and the CO and the CO2 ice features. So there is a wealth of information on the solid matter in a galaxy, in the infrared spectrum. And these are the latest results obtained by JWST, so the James Webb Space Telescope, which was launched 2 years ago. And we have a very detailed spectral information now. But so these broad features are mostly due to organic matters, so polycyclic aromatic hydrocarbons. And this blue spectrum is taken from the relatively star formation active region in a galaxy. But within the same galaxy, so this red spectrum is taken from the central region. So even within the same galaxy, so the spectral shape vary significantly from region to region. And this map shows the 7.7 micron pH emission map for this nearby galaxy. So, so this spectral feature, 7.7 micron pH feature. And so as you can see, not only spiral patterns, but also very detailed structures and many filamental structures can be seen. So the organic matter pHs are widely distributed within the galaxy. And this is our Milky Way, our galaxy. So the pH emission map of our galaxy. And actually, this is our Akari product. So Akari did all sky survey in the mid-infrared and far-infrared. And especially 9 micron photometric band is quite unique to trace the pH emissions. So this is the comparison of the filter transmissions between the Akari 9 micron red one and IRAS and WISE. So as you can see, the Akari 9 micron band traces the pH emission feature, so this blue hatched area very well as compared to the other all sky survey mission, IRAS and WISE. So this map is the only one pH all sky emission map in the world. And by the way, so this is the raw data, raw data. And in the raw data, we see this kind of S-type distribution in the mid-infrared. And this emission is coming from the interplanetary dust. So the dust emission within our solar system. So, and after removing this component, then we get this Milky Way pH emission map. And for example, for this region, so we can see this kind of very beautiful image, filamental structures again. So in the short summary, so by using the infrared, space infrared astronomy spectroscopy, so we can study the fundamental materials like organic matters, water ices, and minerals, so which are fundamental and essential for the presence of our lives, so for our human beings. So this is the introductory part. So I move on to the technology part. So in order to detect very faint signal, infrared signal from the universe, so it's very important to reduce the infrared background as much as possible. So this plot shows the thermal radiation from a telescope with a different temperature. 80K, 45, 20, 8K. And this black spectrum is the zodiacal emission and the galactic cirrus emission. And the zodiacal emission is the interplanetary dust emission. So this component, and the galactic cirrus component is a Milky Way dust emission. And these are natural background. So we cannot escape these contributions. Then the thermal radiation from a telescope. So it's better to have low temperature, as low as possible. For example, 20K. 20K seems to be low enough, but actually this 20K is too high because the thermal radiation is as strong, actually 3 orders of magnitude strong as compared to this natural background. So barely 8K is very okay, or hopefully 6K and below 6K. So the technically it's very challenging. And also, as you know, the atmosphere is opaque in the infrared. So we need a satellite and a cryogenic telescope. And I summarize a history of mid and far infrared astronomy satellites. So here I exclude, actually I do not include the cosmology satellite like Kobe and Planck. So the vertical axis is the telescope temperature, and IRAS started the space infrared astronomy and detected many unexpectedly bright infrared targets, galaxies, and then the ISO followed, and the IRTS Japan mission also followed, and then the Spitzer was launched in 2003, and Akari was launched in 2006. And WISE also did the all sky survey, and the Herschel. So this is the ESA-led far infrared mission. So the telescope, the diameter of the telescope is quite huge. So it was 3.5 meter, but the temperature was 80K. So it's quite high. The temperature is quite high, but it's a huge telescope. Then the JWST, which was launched very recently, and the diameter is 6.5 meter. So this diameter could not be accommodated within a rocket fairing. So the telescope was folded within the rocket fairing. Then in the orbit, so the mirror was deployed. And in parallel, we planned to launch Speaker, but unfortunately, so it was canceled. So now we are promoting the far infrared probe and the GLS Plus, and the target launch year will be in the 2030s, mid-2030s. Then first, so it's very important to select a proper material for cryogenic telescopes, so low temperature mirror. And this summarizes the properties of the material for low temperature mirrors. Vertical axis is the thermal stability, so thermal conductivity divided by the thermal expansion coefficient. And the horizontal axis is the specific stiffness, so Young's modulus divided by the density. And this value, this stiffness is very important to make lightweight mirrors. So for both values, so the larger, the better. So to this direction, the material is better as a low temperature mirror material. So for example, aluminum is not good at all for low temperature mirrors. And beryllium also a metal material. And this has not so good thermal stability. But for some reason or other, so the NASA-led mission, IRAS, adopted this beryllium mirror. Then the following mission, Spitzer and even JWST adopted the beryllium mirrors. And ISO adopted the fused quartz, so the glass mirrors. So actually this mirror is very heavy. And for Akari, we adopted silicon carbide, so the ceramics. And so the diameter was 71 centimeter and operated at 6K. And this SiC mirror was first cooled SiC mirrors in space. And after Akari, so Herschel adopted the SiC mirrors. So the SiC mirror has a relatively good properties as a low temperature mirror material, but I think the CFRP, so carbon fiber reinforced plastic, is the best. But so far, the development is not so successful because of the presence of the carbon fiber, which degrade the surface quality at low temperature. Then we have to guarantee the imaging quality of the cryogenic telescopes. So we have to test cryogenic telescope at low temperature. And this is the case of the Akari telescope. So we use the laser interferometer, but the interferometer cannot be operated at low temperatures under vacuum conditions. So usually we place the interferometer outside the chamber. Then the telescope was installed in the cryo chamber and cooled at below 10K. And we placed the flat mirror, fused quartz mirror at the bottom. And the laser is coming to this way and reflected, and then going back to the interferometer. And this is the principle of the measurement. So this is the telescope side, and then this is a flat reference mirror. And then the beam is divided here, and then this side, the wavefront has an error. And here we combine two beams, and we see the interferometric fringes. And from this interferometric fringe patterns, we can create the wavefront error maps like this. So this is the actual measurement of the Akari telescope, 9K, 45K, and the ambient temperatures. And we saw the significant change in the wavefront error as a function of a temperature. So this value is given in the unit of helium neon laser 633 nanometer. And then the blue is a cool down and red is a warm up profiles. And this is the system requirement level. Okay, so we had to meet this requirement level. So as you can see, there is a significant change in the deformation, and especially at 50K, so the deformation got worse. And then quite unexpectedly, so deformation reduced at below 50K. Then why this happened? So this can be explained by the delicate mismatch, so the small difference in the coefficient of thermal expansion between SiC and the invar metal. So the invar metal was used for the support structure of the primary mirror. So this is the backside structure of the primary mirror. So there is a small difference in the CTE between SiC and invar, and particularly at 50K, you can see the crossover of the CTE. And thanks to this crossover, we got this improvement in the thermal deformation. So we were quite lucky. And actually, the Akari telescope has a diameter of 70 centimeters. But for example, a significantly larger telescope, 1.5 or 2 meter telescope, then we need a 2 meter flat mirror on the bottom side, 2 meter flat mirror, haute collimation flat. But in practice, it is very difficult. It's almost impossible to fabricate the very precise 2 meter diameter flat mirror. So we cannot guarantee the flatness of the mirror surface over the full aperture. So for larger telescopes, so we have to use another technique and called stitching interferometry. And in this case, we prepared 1 meter telescope and 30 centimeter small flat mirror. And by rotating this mirror, we cover the whole aperture of the telescope. And at the same time, so this is a 1 meter, so we can prepare the 1 meter flat mirror. So using the 1 meter flat mirror, we perform the full aperture photometry. Then, so this is the sub-aperture measurements. So many sub-apertures are measured. And then by using the stitching technology, so we got this result. Then on the other hand, so by using the 1 meter telescope, so we got this result. So the both results are consistent. So we demonstrated the validity of this stitching interferometry. But in our case, so we have to cool down this measurement system at low temperature. So using the JAXA 6-meter space chamber, we installed this measurement system. And then the interferometer was placed in the pressure vessel because this interferometer cannot be operated at a vacuum and low temperature. And then we measured the same, actually we performed the same measurement, and this is the vacuum ambient wavefront error map, and this is the thermal deformation between the ambient and the low temperatures. So for large cryogenic telescopes, we need a stitching interferometry at low temperatures. So this is one important key technology. And the other one is the CGH interferometry for instrument optics. So the instrument is also, it has to be also cooled down at the cryogenic temperatures, but instrument optics has much more complicated surfaces than the telescope optics. And in the case of speaker, middle-infrared instrument, so we have to reduce the number of the mirrors as much as possible. And also there's a very stringent requirement on the envelope of the instrument. So we adopted the freeform mirror optics. Then in order to measure the freeform surface, we have to generate the customized freeform surface using the CGH, so the computer-generated hologram. And this CGH is the two-dimensional grating device, so the micro pattern processed device. And then, so for each mirror, we customize this the diffraction wavefront surface freely. And then using this cryo chamber in our laboratory, so we measured the, for example, in this case, an off-axis parabola mirror measured at 10K. So the measurement was successful. And now recently, so we are testing the electric CGH. So this is a mechanical CGH. So we have to fabricate the different pattern, the CGH with different pattern for every mirror. But this electronic CGH, so using the 1K by 1K micro mirror array, we can actually, so the tilt angle of each mirror can change electrically. So we can produce on and off status per each pixel. Then we can simulate the CGH-like pattern. And then this is our recent measurement. So this is a preliminary result, but electronic CGH seems to be working. Okay, so for instrument optics, so space infrared instrument optics, so the CGH interferometry at low temperature is the other important key technology. Yes? 1K by 1K is the 1K, actually the 1000 by 1000, 1000 by 1000 pixel. So the number of the pixels are, yes, 1000 by 1000. Then these cryogenic optics has to be installed in the spacecraft. And then, so this is the conventional mission concept. So we need a large helium tank, and we need a large vacuum chamber, and we can have only small telescope inside. And the amount of the liquid helium for the past missions, so 720 liter for IRAS, 2200 for ISO, 360 for Spitzer, Herschel 2000, and Akari only 180. So in the case of Akari, not only liquid helium, but also used the mechanical coolers simultaneously. Then this starting cycle, two-stage starting cycle mechanical cooler was the first 20K class cryo coolers for space science missions. And based on this Akari heritage, we proposed this cryogen-free concept. So in place of the liquid helium, so we put many mechanical coolers to cool the telescope, and also thermal radiator is put here, and we can get a larger telescope and longer mission life. And so for speakers, so we have two kinds of configurations. So the telescope axis vertical configuration, the horizontal configuration. And for both, there are pros and cons, but we have a thermal design which meet the system requirement. And this is the horizontal speaker case. So solar radiation is coming from the bottom side, and then the bottom side has a high temperature, ambient temperature, and we have several thermal shields called the V-grooves, a telescope shield, and a telescope baffle. And this telescope baffle is the temperature is 5K. So ambient temperature to 5K. And this is the thermal flow. So I skip the details, but these numbers are heat flow given in the units of milliwatt. And at high temperatures, so these values are very large. And then the radiative cooling is effectively working at high temperatures. And at low temperatures, radiative cooling doesn't work. And this mechanical coolers is very important to cool this part. So this design meets the requirements, but this is just the design and the simulation. So we have to demonstrate hardware-wise for future far-infrared and mid-infrared cryogenic missions. So this is the status. Then I move on to science part. So I focused on the uniqueness of the space infrared spectroscopy. So the solid state matter or solid state physics in space. So in connection with this point, so I'd like to select this topic. So the mineralogical study of interstellar dust in a galaxy. And I choose the AGN galaxy. So the active galactic nucleus galaxy. And this galaxy has an active supermassive black hole in the center of our galaxy. And this is a generally believed standard model. So the black hole is in the center, and the jet is producing this direction. And then we have the dusty torus surrounding the black hole. And in particular, in early evolution phases, so these systems are known to be deeply embedded in dense clouds. Then when we observe this kind of targets, then we get this kind of spectrum. So the hot dust continuum emission is here, and this continuum emission is coming from the center of dust. So the dust closest to the central AGN, so heated up to high temperature, and then the dust present in the dense clouds absorb this continuum emission. And in this case, we see the SIO stretching absorption mode and OSIO bending absorption modes. And by studying the details of these absorption features, we can understand the processing of the silicate dust, and which is closely related to the AGN activity. And these are 4 examples. So as you can see, there are significant variations in the absorption profile of silicate. For example, this galaxy shows a sharper absorption features, and this galaxy shows a round shape absorption feature. So actually, the variations are quite significant from galaxy to galaxy. Then, based on the Spitzer 5 to 30 micron spectra, we carefully selected the 98 heavily obscured AGNs. And we perform systematic study of silicate surrounding AGNs by detailed modeling. And I skipped the details, but I briefly give you the overview of our structural model fitting. So this is the fitting model. So the first component is the host galaxy. So we have a pH emissions. So as I explained in the earlier part, so the organic matter emission from the host galaxy, and the dust thermal emission from the host galaxy as a whole. So this is the first component. And the second component is the emission from the circumnuclear, so central dust and circumnuclear dust clouds. And this component is a black body radiation with the temperature of 1000 K. And the 1000 K corresponds to the sublimation temperature of silicate. Okay, so this is the maximum temperature. And this 1000 K radiation is absorbed by this exponential component. And tau shell is the dust opacity, so the opacity of dust in the circumnuclear clouds. And dust itself emits the thermal infrared radiation. So this is the dust emission component. And these components are absorbed by the water ice. So the water ice is located the outermost region of the central cloud, dense clouds. Okay, so these are pH features, and these blue hatched area is the absorption features, and these deep absorptions are due to silicate minerals. Then for the distribution of dust, so we assume dust in a spherically symmetrical shell heated by a central AGM, and we assume the dust distribution, the power law function as a radial profile of the dust density. So the power law index P and optical depth tau, and Y is the ratio of the outer to inner radius. And we assume the 4 kinds of chemical compositions of dust. So amorphous olivine, amorphous pyroxene, crystalline olivine, and amorphous carbon. And we changed these ratios to fit the spectra. And other important parameters are dust porosity and dust sizes. And I skip the details, but so as far as the dust properties are concerned, we have 4 parameters: crystallinity, so crystallinity, and olivine pyroxene ratio, and porosity and the size. I'm afraid so most of you are not so familiar with this terminology, olivine and pyroxene. And actually, these are main silicate minerals, not only in space, but also on Earth. And olivine and pyroxene have different crystal structures like this. So this tetrahedron is SiO4, and this SiO4 is so not connected for olivine, but for pyroxene. So this structure is connected here. And also in the space in between, so the magnesium or iron atoms are there, but the relative abundance of the magnesium and iron to the Si is low for pyroxene than for the olivine. And so this olivine and pyroxene is very important for the differentiation of magma phenomenon. So this is a volcano, and under the volcano, so there is a rising magma. And here we observe the differentiation. So due to the difference in the crystallization temperature. And olivine has the highest crystallization temperature, and then the pyroxene. So first, the olivine is crystallized. Then afterwards, the pyroxene. And finally, quartz was formed. Quartz was a pure SiO2 mineral. So this kind of differentiation is observed under the Earth, but also near the AGMs. So that is my point. So I briefly explained the spectral characteristic dependence of each parameter. Crystallinity, if the crystallinity is high, then the absorption features become sharp, and also pyroxene ratio, so shifting toward the shorter wavelengths, porosity, longer wavelength shift, and size distributions, so the peak is suppressed. So by studying the detailed structure of the absorption features, we can obtain these parameters for the properties of silicate dust. So this is the result. So one example for spectral fitting. So as you can see, the fitting is extremely good. So our model reproduces the observed spectra very well. So the black data points are observed spectrum, and the red one is the model spectrum. So fitting is very, very good, very good. So this is a comparison with the past results. So there are 2 past results for this galaxy, but fitting was not so successful. So difference is very, very clear. Okay, so actually, so this not good fitting is due to the properties of dust. So they did not adapt the properties of silicate to the observed spectra, just using the silicate dust of Milky Way. So the Milky Way dust cannot reproduce the spectrum. So we have many spectra, and we fitted each spectrum by our model, and fitting was successful for all the 96 galaxies. Okay, so you can see there are variations from galaxy to galaxy, and also the sharpness, very sharp or round shape. And then so these emission features are due to pHs, and these absorption features are due to water ice features. So many pieces of information is included in this spectrum, but our spectral fitting was very successful. Then, so these are main results. So for the crystallinity and the pyroxene mass ratios. So this histogram is the crystallinity, and this one is the pyroxene to the total amorphous silicate. So as you can see, there is a wide distribution for both parameters, especially crystallinity widely ranges from 0 to 14%. And for the pyroxene ratio, so the most of the AGNs show low pyroxene mass ratios, lower than 10%. Then discussion on the crystallinity. So this is the level for the Milky Way dust. So the Milky Way dust show typically 2% crystallinity. So the AGN dust shows a crystallinity significantly higher than that of the Milky Way dust. So which indicates the thermal processing in high temperature environments. So in the regions close to the AGN activity. But these features are detected only in the absorption, not in the emission. So which indicates that the silicate, crystallized silicate currently exists in the low temperature environment. So the likely scenarios are, so the silicate was crystallized in a central region and then transported to outer regions, or alternatively, the silicate was heated and crystallized in situ in outer regions by AGN shocks, actually shocks via AGN outflow. And next, the pyroxene mass ratio. So this is the level for the Milky Way interstellar dust. So the 15% is a typical value for the pyroxene mass ratio. So the AGN dust is obviously pyroxene poor. So which indicates that so the silicate is fresh. So as I explained in the magmatic differentiation. Okay, so the olivine rich. And also 95 out of the 98 AGNs prefer a small sized porous silicate dust. So I skipped the details about these parameters, but so the most AGNs prefer the small sized porous silicate. So AGN obscuring dust is mostly fresh and small sized porous grains recently produced by stars in a host galaxy. Then our original motivation is to understand the cause of the variations in the silicate properties. And these are crystallinity and pyroxene mass ratios plotted against tau 10. So tau 10 is the optical depth of the silicate absorption feature at 10 micron. And the color is the optical depth of the water ice. So the blue is a water ice rich, and the red is a water ice so red is the water ice poor. So as you can see, there is a systematic difference between the water-rich targets and the water ice poor targets. So this difference, so the abundance of the water ice can contribute to this variation to some extent. Then how does this mean? What does this mean? So this is our interpretation. So this is a cross-sectional view of the central region. So the AGN is here, and the dusty torus is here, and this region is exposed to the AGN activity. So silicate is more crystalline rich, and also the silicate is processed thermally, and then the silicate becomes pyroxene rich in this region. So the AGN activity is exposed to this region is exposed to the AGN activity. But on the other hand, so this region is shielded by this dense dusty torus. So low temperature, so the water ice can be present, like snow line in the planet-forming disks. So viewed from this direction, water ice is not so visible, but crystalline rich and the pyroxene rich silicate can be observed. So that's why the water ice poor targets show high crystallinity and high pyroxene mass ratio. So this is one factor, but moreover, we have the global trend, so the decreasing trend for the with tau 10, both the crystallinity and the pyroxene mass ratio. And tau 10 is an indicator of the aging evolution. So at early stages, so the clouds are dense, so tau 10 is large, but at later stages, so the clouds are sparse, thin, so the tau 10 becomes small. Then with this evolution time scale, so the AGN activity will be declining, and these regions, so crystalline rich and the pyroxene rich regions, is disappearing. So that's why, so we can explain this decreasing trend with the evolution time. So in a short summary, so there are at least two factors to explain the variations in the silicate properties. One is this anisotropic distribution of the silicate properties affected by the AGN activity, and also the strength of the AGN activity, so the different evolution stages. So our study covers the high luminosity and also low redshift area. And then with JWST, so we are now studying nearby fainter targets. But more importantly, so higher redshift targets is important to understand the evolution of material for the cosmic timescale. Then this wavelength range is corresponding to this 30 to 180 micron at redshift 5. And also, in order to study very faint, broad spectral features, we definitely need low temperature telescopes. So far infrared cryogenic telescopes are very important for this kind of study. So solid state physics in space. So finally, yes.
So this is about when you looked at spectral luminous infrared AGN. Okay, so
Many of them were having, Jansky kind of.
Yes.
So in this sample, there were any scenarios where, they were having binary black holes rather than a single black hole. Any possible candidate?
In this case, the single black hole.
Okay.
So the supermassive black hole, but a single agent.
So there were no possible, there are several AGN which pose that.
No possibility about.
Are there anyone looked at
Groups.
it and see whether this kind of PAH emission can be different if you have a companion black hole?
No, I don't think so. So
Okay.
the pH is located relatively far side from the central region.
Okay. Okay.
Actually, if the pH is located very close to the center, then the very energetic radiation will destroy the pHs.
Okay.
Too
And-
strong.
Yeah, and that's so the connection to the OGN activity and the ratio, that's very impressive. That's a very good indicator, kind of a different measure. So you talked about possibility of water having,
Water ice. Yeah.
correct. So are there any one of these AGNs, did they actually were showing, because these are high luminosity, any water maser activities were seen in any of these samples?
Yeah, we are now studying the JWST data, using JWST data. And
Oh.
I'm sure the weak water ice absorption
maser-
features.
Maser actions?
Yeah, but still under investigation.
Okay.
Uh,
Yeah.
But
Thank
this
you.
is our unique, actually, our original idea
Yeah.
using
it's
this
very
water
impressive,
ice
yeah.
absorption features.
Yes.
And then,
Yeah, thank you.
okay, then I close my talk with a future prospect. So 3 years ago, so NASA issued the decadal survey report, and they recommended a far infrared mission. So at that time, so it was just after the cancellation of Spica. So in several places, so Spica was explicitly mentioned in their report. So their conclusion is, so we need a properly scoped far infrared probe, and then in a extremely timely manner. Okay, so we need a far infrared mission in place of the Spica. So following this report, so the fine infrared probe mission was considered, and the proposal was already submitted last year, the end of last year, and we have now 3 mission candidates, and I explain later. And down selection will be done in the end of this year, and the final selection will be done in 2 years from now, and the target launch year is 2032. I'm afraid it's a bit schedule. This schedule is tight. So we proposed a cryogen-free cold infrared mission concept for SPICA. Initially, SPICA has the telescope diameter of 3.5 and the temperature was 6K. But after the great earthquake in eastern Japan, so we have to descope the SPICA. So the size was 2.5 meter and 8K. But during the coronavirus pandemic, so the SPICA was canceled. And now, so we have 2 waves. So on the fine infrared side, so the NASA-led fine infrared probe missions so are being promoted. And there are 3 candidates, Prima, FAST, and Saltus. And these 2, Prima and FAST, have a quite similar mission concept to SPICA, so cryogen-free SPICA-like missions. So we are contributing to these missions. And actually, the JAXA ISAS issued a support letter for Prima. Okay, so our first priority would be Prima for our, actually, as far as our contribution, international contribution is concerned. And on this, sorry? No, 14 meters. Okay, so Saltus is the inflatable mirror. So this is folded in the rocket fairing and in the orbit, so they inflate the mirror 14 meters. So they do not guarantee the image quality, just a photon bucket for this mission concept. So anyway, the mission concept is entirely different between the Saltus and the other 2. So, and we have the Japan-led mid-infrared mission called the GLEX Plus. And requirements are not so stringent as compared to the fine infrared. So you have a 1.2 meter and 50K, but we adopt the cryogen-free mission concept like SPICA. So using these future fine infrared and mid-wave infrared missions, so we'd like to study the full infrared spectra of galaxies over the cosmic range. And particularly for me, I'd like to see the spectrum of the fast dust. So water ice or graphite or quartz, nobody knows, but I'd like to see the fast dust spectrum. And then the fast organic matter spectrum is also my interest. So I'd like to see the fast organic matter. So how does this fast organic matter look like spectroscopically? And this is the other science topic. So I skipped this topic. So from planet forming disks, but this is also very important. And we expect very complicated spectra from this planet forming disks. And I think the most important science case is the snow line, the location of snow line using the water spectra, water lines, and the water spectral features, and also the measurement of the gas and water contents within the disks. And we can also do the ice and dust mineralogy, not only olivine and pyroxene, but also calcite, dolomite, so low temperature minerals. So we can probe the raw mineral of exoplanets. So I'll summarize my talk. With mid and fine infrared spectroscopy, we can get a wealth of information on the material in space, like organic matters, minerals, ices, and so on. And key technology is a cryogenically cooled space telescope and optics, which are to be evaluated with stitching and CGH interferometry at low temperatures. And we propose cryogen-free mission concept for SPICA and for future mid and fine infrared missions. And the scientific part, so I talked about mineralogical study of dust in AGMs, and we have found that silicate is mostly small sized and fresh. And then there is variations in the crystallinity and olivine pyroxenations, and these parameters seems to be changing through processing of the activity of the galactic nuclei. And finally, future prospects. So we are promoting fine flat flow missions and GLX Plus missions in the 2030s, and which will reveal the whole story of the evolution of the material in space from the early universe to planetary system formation. So that's all. Thank you very much for your attention.
Thank you, Kaneda-san, for a very beautiful presentation of future of the cryogenic space telescopes and the potential, discovery potential of these instruments. Yeah, so the seminar, the colloquium is open now for discussion. Yeah.
This cryogen-free platform. Now, two major challenges, at least early days of Stirling coolers, was too much power requirement and also lifetime of the moving parts. So how they have been improved now to enable such missions that you talked about?
Okay, so the efficiency of the cooling, for example, there is some actually improvement, but the most important point is not the power, not the efficiency, but the reliability. For example, the lifetime of the cooler, and we are continuing to continuous testing of the mechanical coolers. So now the 5-year lifetime is guaranteed according to our cryo cooler testing. But actually about this cryogen-free mission concept, the most important point is actually the optical surface, actually that optical parameter of the surface. So how to control the surface of the thermal shield, for example, the emissivity, at low temperature emissivity is quite difficult to measure. So we need a very precise measurement of the emissivity, for example, at low temperatures. And we have some technology to customize the emissivity. Honeycomb structure like surface can be actually can change actually using the honeycomb surface. We can customize the emissivity value at low temperatures.
Thank you. I have just one curious question. So the deformation that you see in the silicon carbide mirror when you cool down, is that primarily driven by the inhomogeneity in the mirror or the difference of material that is holding it? Like INVAR versus the silicon carbide differential thing.
Okay.
Because if it is the difference, then can you make the entire thing out of the same material?
Yeah, actually, the silicon carbide has a very high thermal conductivity. So actually, the temperature gradient is very, very small. And the temperature gradient is very important for the uniformity. Actually, if there is a inhomogeneity in the temperature, then that will cause the local deformation. So the thermal conductivity is a very important parameter, but also the expansion coefficient, so CTE. So the homogeneity of the CTE is also very important. And in the case of SiC, there is no inhomogeneity.
Okay, so the deformation that were primarily driven by temperature gradient.
Temperature, yeah, stability. But the specific stiffness is also very important for the space telescopes, because we cannot actually fit very huge telescopes. So we have to reduce the weight as much as possible. And in the case of Akari, the weight is only 30 kilograms. The whole system weighs only 30 kilograms.
I just one more question.
Yeah.
So on the AGN, where you have the higher crystallization, so how important are the star formation history of those surrounding galaxy, like in the supernova? Can they have crystallized it
Yeah. Actually, we see for some galaxies, so pH features, we detected the pH features, and the pH features are mostly believed to be the star formation tracers. So for some galaxies, so for example, this galaxy, so these are clearly see the pH features. And as far as this galaxy is concerned, there is also a star formation activity in the outer regions.
They are not correlated with the crystallization in it.
Actually, it is slightly correlated.
Okay.
That is a very interesting point. So the host pH in the host galaxy is also affected by the Asian activity. Not significantly, but we at a weak level. So by carefully checking for example, the center of the feature, then we see a significant change in the central position of the pH 6.2 feature with the activity of the AGNs. And also the water ice absorptions. So the edge on or face on, so viewing angle difference, so the spectra can change pH features. Yeah.
Thank you.
Thank you.
Nice talk, Professor. So I have one question about the stitching interferometry which you did. So you said that you did stitching interferometry because your surface finish, you did not get the desired surface finish of the mirror. And instead of that, you kind of rotated your mirror and around. So are you saying your wobble in the rotation is less than the surface finish which you were able to achieve? Because while rotating, it can have an action, it can have a wobble, right?
Yeah, motor, yes. We have to guarantee the performance of the motor. But at the liquid nitrogen temperature, that motor is available.
No, not water. It's like when it is rotating, your axis also can wobble, right?
Yes.
So that
bearing, bearing. So we have a special bearing.
Okay, so that ensures the wobble even below your surface finish.
Yes. But actually, a 10K operation, the 10K operation is a bit difficult. So in this case, so this moving part will be placed at 77K. So the liquid nitrogen temperature. And liquid nitrogen temperature, so there are several choices for the motor and also the bearing. That's very good and very important points. Thank you very much.
In your case, this biomechanical system with you have a thermal dissipation shield outside. So how much heat you are expecting to be dissipated from the system?
The shield of the cryo chamber?
Yeah.
This test, for example?
Yeah, you have this shifting from the liquid helium to the...
So from which temperature to which temperature? So it depends on the temperature stage. So okay, so at least 1 watt or so at low temperature. So we need it's a very difficult question. But at which temperature? So 10K?
10K.
Energy dissipation at 10K.
Okay. So
then several hundred milliwatt or so.
So it would be very high.
So
So how are you managing?
Using so in this case, the mechanical coolers and liquid helium. So actually, okay, so depending on the availability of the liquid helium, so now the supply of the liquid helium, so you have a problem on the supply of the liquid helium. So in that case, we can use the mechanical coolers. And for other cryogenic missions, so they are thinking about they're thinking about using the mechanical coolers, so the 4K cooler. And then by using many mechanical coolers, then we can dump the heat of the several hundred milliwatt.
Okay, sorry. Palak, please go ahead. Palak.
Yeah. Um, yeah, thank you. It's a very interesting talk. You have mainly talked about AGNs and the mineralogy and crystallinity of silicate dust around AGNs. Of course, AGNs are very bright objects, but they're also very far away.
Yes.
Do you know of instances of use of this kind of technology for doing the similar kind of things for locally bright objects, like, not so far away, but there are supernovae which are happening not so far away, perhaps.
Yeah.
And then we also have all this dust formation.
Okay, thank you. Yeah, that's a very good questions, I think. And in the case of supernovae, so we have to think about the shock processing of dust. And dust is very fragile against the mechanical shock. So, but in the case of the AGNs, so the shock is not so strong, but energetic radiation works for changing the properties of dust. But in the case of supernovae, it's too actually energetic. So the most of the dust will be destroyed.
Most of the dust will be destroyed nearby, but there is a phase, and when the dust is far away from the actually supernova in the circumstellar medium, when the dust is actually irradiated and illuminated by the supernova.
Okay, yeah.
And so, by using the techniques that you're talking about, it should be possible also to study that kind of dust, which is from the circumstellar environment and from the early history of the stellar evolution before the supernova explosion.
Okay.
So my question is, this kind of thing must have been used, but I don't know, even though I work on supernovae, but I'm not really aware of it. So have you heard about this kind of thing?
To my knowledge, there is no such studies, I think.
Okay.
My knowledge. Right. It's a very interesting point. But actually, this is a niche study. Niche study.
Yeah, thank you.
Very interesting. Study the mineralogy of dust. But anyway, thank you very much for your comments.
So thanks once again, Kaneda, for very, very nice, interesting colloquium. So thanks once again. So please join us for a cup of tea at the canteen, West Canteen.
Thank you very much. It's